And where we left off was in kind of looking at these axioms of probability. We looked at the commutative property and the associative property. I think those are pretty straightforward. They tie very easily in terms of union and intersection. But today we're going to look at a few that are maybe not quite as intuitive, and these are going to involve both unions and intersections. And let's start off with the distributive. And we can see this in two forms. Let's say we have A, B, and C, right? We've got A, B, C. If I say A union B intersects C, and I'm just going to put parentheses around that to be very clear what's happening there. The intersection operation is going to precede the union operation in terms of order of operations, but we don't have to worry too much about that. I'm going to very clearly delineate anything like that using parentheses. So there is an equivalent statement here, and that is A union B intersected with A union C. I think for some of these it's nice to sort of walk through verification of it, and we can do that pretty easily. Let's say A is true, B is false, and C is true. And keep in mind that this will apply. This will be equally valid if A is a set, right? If A is a set of objects, right? Like object 1, 2, and 3, so on. And B is a set of objects, C is a set of objects. This property will still hold true. But I just want to verify, so I'm just going to verify this through looking at it as if it's solely a Boolean expression. But it will work for sets as well. So I'm going to go ahead and substitute these. A is true, and I'm just going to use a capital T. That's going to be unioned. Instead of using union, I'm going to replace union with or. Okay, and so B is false, ANDed with true. Okay, and then we can fill these ones in as well. So true or false. ANDed, I keep writing intersection, but ANDed with true or true. Okay, and we can process this, and I think the takeaway from axioms of probability that I really want you to have is an understanding that you can walk through and process these, right? So let's look at this first one, false and true. Well, the AND operation has to be true on both sides for it to be true. So false and true is going to yield false, leading us to true or false. Well, for or, it has to be true on at least one side, right? And it is right here, so we can simplify that to true. Okay. If we walk through this, true or false right here, that is going to be true. It's going to be ANDed with true or true, which is true. True and true is true, and we can see that we have some verification of this distributive property. I won't write this out, so this is still the distributive property, but I want to show you the other form this can take. We can say A intersect B or C, B union C, and this will be equivalent to A intersect B, and that can be unioned with A intersect C. So, same pattern, we've just swapped the union and intersection, and if we were to write this out, we could say A and B or C is going to be equal to A and B or A and C. So this is going to hold true. We could fill those in, but I think you get the idea here. At any rate, we can fill in Booleans and simplify an expression down, and that's kind of what I'm driving at here. If you were to work through all of these axioms of probability, and really work at them, you might start seeing that there are ways to simplify Boolean expressions or set operations, for that matter, right? These are things that can be simplified, and that leads us into, well, some more explicitly simplifying laws. Okay, so that was the distributive property. There's also this thing called the idempotent laws, and there are two that we're going to state here, but there are other things that I kind of think of as being idempotent laws, but these are very straightforward. A union A is going to be A, right? That just makes sense. A unioned with itself is going to be itself. That's not too surprising. And then if we intersect A with itself, that will also be A. So these are two things, two ways that we can simplify this, simplify an expression. So if you ever see A union A, and this is an expression standing on its own within a larger expression, if you can operate on that expression, it is irreducible to A. So that one is a bit of a tautology. There are some other obvious things. So those are idempotent, and then we have these ideas of domination. So we've got a couple domination laws. And I introduced these actually yesterday, but I didn't name them as such. So if we intersect any set with the null set, which we can represent like that or like that, either way, if we intersect any set with the null set, we're going to get the null set, right? A intersected with something that doesn't have anything is going to be nothing. It's not going to have any elements. We can also union with what we think of as the universal set, which we can represent in a couple ways. We've been representing it with a capital S. We could also use omega, right? Often we will use a big capital U for universal set. But let's just say that this is S. This is the sample space that contains A. This is just going to be A. I think that makes sense, right? If we union, if we intersect, I should say. If we intersect this with the sample space, we should get A. Now, if we union it with the sample space, right, that's a different kind of domination that we might see. A unioned with S is going to equal S. I think that makes sense, right? You union anything with the sample space, well, you get the sample space, or universal set, however you want to think about that. So there are some other laws that can come in handy in, we're thinking about this more in Boolean operations, but again, these also apply to set operations. There are different laws that we think of as absorbing. So these are absorption laws. So if we take A and union it with the intersection of A with B, well, let's name these and let's see what we get. So A, let's say A is true, B is false. I think we'll just use the same thing we used before, and C is true. Let's fill this in. So this is true. We'll use or instead of union, and this will be true and false. So true and false, well, that's obviously false. True or false is true. So it turns out, if we're thinking about this as a consistent form, it turns out that this will actually equal A. So A, what we can take away from that is A union A intersect B is going to just be A. So we can absorb B into A if we perform this kind of operation. We have another absorption law. That operates very similarly, where A intersected with A union B is also just going to equal A. I could walk us through that, but I think you get the idea here. We have reducible operations, and we can represent these, again, we can represent these as Boolean expressions as easily as we can represent them as set operations. One that may be sort of obvious, this kind of fits with the idempotence, but we call this the identity property. If we union a set with nothing, that's just going to be that set, right? I think it's kind of obvious. But it's one of our laws, and so, just pointing it out. So let's look at a couple more. So these are sort of big laws. These are what we call complement laws. And they're somewhat grandiose. If we say not, if we take the complement of nothing of the null set, that is going to equal the universal set, which I've been representing for our purposes with S. And if we say not the universal set, that's going to be the null set, a set that contains nothing. So again, I think these are obvious. Let's look at some that are, let's look at a related law first, the involution law, which has the feel of a complement law, and I think this is going to be sort of obvious. Not A, right, is just going to be A, just a double negative, and these eliminate out, and we get the original A. So there's this law that when I was doing comp org, when I was doing circuit design, there's this law that comes in very handy that I don't know the name of, and as many times as I've taught this in this course, nobody else has recognized it. Often we'll have like EE people in here or comp sci people who would have learned, set reduction or circuit reduction. But this looks to me to be a lot like an involution law, an absorption law. And I don't know what it's named, but I think it's pretty cool, and we can demonstrate it. This is one of those really useful ones if you ever find yourself doing circuit design, which I doubt you will anytime soon. But you might be reducing Boolean expressions at some point, or queries, like SQL queries, optimizing SQL queries, where this stuff does sort of come in, or starts coming in handy. So A intersected with B, unioned with A intersected with not B, and I'm going to put the not above B in this case instead of writing it out. Well, let's work through this. So A is true, B is false, and again C is true. And let's just figure this out. So this is going to be true and false unioned or ORed with true and not false. Okay, well, let's work these out. First, we'll take care of this not false and turn it into a true. And then we can see true and true. Well, that's true. True or true and false. Well, that's false. But it sort of doesn't matter because we've got a true on this side, so we can reduce this out to true. Turns out this is just A. And we can see that this whole expression up here is reducible to A. Now, what does that mean? Let's say you have a few Boolean parameters to a function, and you find yourself with this, essentially this type of expression happening within your function in order to make a choice. Well, at the end of the day, whatever that value of a is that you pass in, whatever that is, that's all you need to answer, to perform that logical operation within the function. And you can reduce out the need of having b in here at all. And, that may not be entirely necessary for most functions you write, but there are going to be times where there is a better function with a simpler logical structure. And this brings us back to where we ended yesterday, which was with De Morgan's laws, which, if you're not going to remember anything from these axioms, except for De Morgan's laws, that's fine. You will need to know De Morgan's laws at certain points. That will happen. If for no other reason than somebody in a job interview is going to make you walk through a De Morgan's law problem, that is not out of the question. That is the kind of cruel thing that people, when they're hiring, do. So let's just look at the first law. So these are De Morgan's. And this first law is going to be A union B. That expression is knotted, so that whole expression is knotted, A union B. In order to untie this expression from being underneath this knot, we can say this is just knot A intersected with knot B. We can prove this. Let's say A is true, B is false. We can prove this pretty quickly. This is true or false. Is that going to be equal to not true? So not true and not false. Well, let's find out. True or false, that evaluates to true. Not true is going to be false, and not false. What did I do wrong here? Oh, I'm sorry. This should all be knotted. My bad. That should be a false. There we go. That makes way more sense. False equals, this is false, and not false is true, but that doesn't matter. False and true evaluates to false. We can see that those two expressions are equivalent. The other De Morgan's law is, looks very similar. So these are De Morgan's laws. The other one is A intersect B. That expression, knotted, is going to be not A, or I should use union here to be consistent. Not A unioned with not B. And again, if A is true, B is false, we can fill this in and see this is going to be true and false, and that will be knotted. This will be not true or not false. Not false evaluates to true. Not true evaluates to false. False or true evaluates to true. And true and false, well, that evaluates to false, right? But we want to make sure to recognize that there's a not statement that encloses that. And so not false, well, that's obviously true. So we can see that that holds. So there's a concept here. That's a great question. How would you type the not bar in De Morgan's law in Slack? This is what I would do. And I know this is not going to be very satisfying, but what I would do is not A union or sorry, yeah, I'd have to copy the symbol. So if I was to have to write this in Slack, I would probably do this. Not A intersect B and putting it in parens. You know, it would be, for me, it would be more about just communicating it. You know, like this is the operation that I'm trying to be clear on. If I wanted to copy the intersection symbol from somewhere online, you know, like some big library of symbols, that's possible. I think there's actually a key combination for it, but I wouldn't worry too much about that. If you are dealing with these expressions in a form that is, you know, mathematical, symbolic math, instead of Python, then you're probably going to do it on pen and paper, or again, you're going to be using MathJax or LaTeX in general. That's just really the way forward. At some point, you're going to want to learn MathJax, and then at some point later, you're probably going to get started in LaTeX. So that's how we'll usually write these out. Okay, so there's this concept that I'm just going to introduce very briefly. There's the concept of circuit design, and there are logic gates within circuit design. And I'm just going to show us a few of these. And yeah, typing not A and B, that will be equivalent unless you're talking about a set. So if you're talking about sets, then you're going to want to be explicitly stating intersection. But you know, that just applies for sets. If we're talking Boolean operations, not A and B is completely valid. Okay, sorry. That was a little bit of a diversion for just a second there, but let's talk about logic gates. If we think about a function that has Booleans, you know, that are deciding the flow of code in that function, then in a lot of cases, we can think about that as sort of being like a circuit. And we have these equivalent gates. We have gates that we can use to visually design a circuit. This is going to be just a logical structure. So for AND, we have what we call an AND gate, and it looks like this. And this is going to be A, right? Here's our input A, here's our input B, and here's our output. In here is the A and B, right? So if A receives true and B receives false, of course, the output of this is going to be false. If A is true and B is true, the output is going to be true, right? This is just a visual representation of the same kind of thing that we've been talking about. And we can think about the resulting truth table, or what we call a truth table. And we can design that very simply. This will be A and B. So how many potential outcomes do we have? Well, we should have 4, right? Where we've got, and here you might notice, we're going to count in binary, 0, 0, 0, 1, 1, 0, 1, 1. We'll get much more into binary later. 0 and 0, we can think about this as false, false. That's going to yield 0. 0 and 1, well, that's false, true. That's going to, you know, get us false or 0. True and false, or 1, 0, is going to get us 0. The only instance here that gets us a true is if we have 2 true inputs. So we can see this idea of a truth table related to the gate. And we don't just have the AND gate, we have OR gates. And these look a little bit different, just slightly. They have a curved angle here. But it's the same idea, right? We've got, if A is, well, we can still do this thing where here's A, here's B, 0, 0, 0, 1, 1, 0, 1, 1. And we can kind of see that this is the inversion of the AND gate, where 0, 0 is going to be 0, 0, 1 is going to be 1, 1, 0 is going to be 1, 1, 1 is going to be 1. So we have a lot more options of passing a positive signal in this case. And let's see, we've got the idea of a NOT gate, okay? So this isn't really a gate, it's kind of a modifier. So whatever this gate is here, we'll think of this as a triangle. We're going to put a circle to say NOT. And so you can see if that's the case, then we have this idea of a NAND gate, which is just AND with a NOT on the end, right? So we can think about the truth table here. If this is 0, 0, 0, right? If we've got 0, 0, that's going to evaluate in AND, is going to evaluate to 0. Then we NOT that, and we get 1. 0, 1 is going to evaluate to 0, NOT that, and we get 1. 1, 0, right? Again, we get 1. 1, 1, we get 0. Now that seems a lot like an OR gate, right? Seems very, very similar. However, notice that if it was an OR gate, then this 0, 0 would have evaluated to 0. So we've kind of turned this on its head a bit. Okay. All right, so we've got, just a couple more ideas of gates. And these are just, again, these are just another way of representing logical structures. So we've got NOR, which is going to be, just like this. I won't run through exactly what that does. But let's think about one other gate, which is an operation that maybe you've seen or maybe you haven't, and that is the XOR. XOR is pretty interesting. So it kind of looks like an OR gate, but we have just an extra line here. And what XOR is going to tell us is whether or not A and B are different. If A and B are the same, it's going to return a low energy signal or a false, however we want to think about that. If A and B are different, it's going to return a 1 or a high energy signal, however you want to think about that. So the truth table for this, and this is XOR, which we do a little cross within a circle. If we have 0, 0, well, those are the same, we get 0. 0, 1, those are different, we get 1. 1, 0, we get 1, because those are different. 1, 1, those are the same, so we get 0. XOR as an operation comes in very handy in a lot of cases, but we're not going to, mess with it beyond just showing that this operation exists. And if you perform an XOR as a Boolean operation, what you're really asking is, are these two inputs different? Okay. So let's, we're about 30 minutes in. Great. Perfect. Sometimes I'll, at this point in the class, I'll design a circuit, actually, and run values through that circuit. But I'm going to leave this as it is. It's more food for thought. You're not going to see this on the technical interview by any means. Where you might encounter it is when you're looking for logical structures, when you're Googling, things like that. Pretty much what I want to say about this is that it's easier than you might think. Right. You might be building Carnot maps. Yeah. There is a whole sort of underlying technology that, or underlying set of operations that at a later date you are going to start becoming familiar with. And that's more on the computer organization side. It relates very heavily to logic, and especially if you're working in optimizing SQL queries, things like that, you're going to learn these kinds of circuits. It's going to start becoming very important at that stage. At this stage in programming, in technology, where you're at, probably you won't be applying this very often, but we like to just go over it in a kind of cursory way. Okay, so let me track down the next thing that we're going to talk about. Just one moment. So we're going to talk about basic probability. And we've laid the foundations for considering basic probability. Let's see, where is this? It is, oh, it's just the next set of slides. Okay. Okay. So we've already touched on most of this, and I think we can move through this pretty quickly. We'll start off with this idea of cardinality. Let's say we have a set, A. And within A, we have cat, dog, and bird. The cardinality of this is 3. Now, why is it 3? It's 3 because there are 3 items. Pretty straightforward, right? If we have a sample space that includes, I'm just going to put single letters for these: a cat, a dog, a bird, a pheasant, an eagle, and of course a shark. And we're asking a question like, well, what is the probability of choosing a cat, a dog, or a bird? One of those, right? What is the probability of choosing something from A? That's pretty easy. That's just going to be the cardinality of A over the cardinality of S. And a lot of things are going to come down to this very simple expression. It's the number of items in our subset divided by the number of items in the containing set. So that is pretty straightforward. We can think about the cardinality as being the magnitude of the set, the number of elements that compose it. So A is a subset of S with a cardinality of 3, and S has a cardinality of 1, 2, 3, 4, 5, 6, and so we can see that the probability of A over S is actually just going to be 3 over 6, or 0.5. So let's look at a simple example of this. Another simple example. And we're always talking about rolling dice. Why not? So if we have a die, and I think we looked at pretty much the same idea yesterday. We have a die. It can 6-sided die. This can be 1, 2, 3, 4, 5, or 6 pips, as we call them, right? A pip is just one of these dots, right? If we're talking about the event A as being an even number of pips showing, then A is going to be composed of 2, 4, and 6. And very simply, we can ask, what is the probability of A? That's going to be the cardinality of A over the cardinality of S. And of course, that is 3 over 6 or 0.5. Very, very straightforward, right? This is very intuitive at this stage. This is very intuitive. So I did this P of A thing here, and maybe we should step back a little bit and talk about notation. This just means the probability of event A occurring. We can ask other questions. What is the probability of not A occurring, right? We can ask that. We can ask the probability of A intersect B occurring. We can ask the probability of A unioned with B occurring. And then there's this sort of big special one that we're going to think about a lot in, I believe, our last lecture before our technical interview review. We can think of the probability of A given B has occurred. This one is pretty special, and this gives us, sort of the motivation toward conditional probability, which, we're going to devote a lecture to. You don't need to know conditional probability for the technical interview, but it comes up a lot. There's a whole pretty much branch of statistics that includes concepts related to Bayesian thought, right? Bayesian approaches, Bayesian thought, Bayesian models, and from this small statement right here, we can extrapolate what we call Bayes' theorem, which we're not going to do today, but we will spend at least half a class on Bayes. We might, hopefully we'll be able to dedicate the whole class and get you all started on Bayes' theorem and conditional probability through that lens. Okay, so we've already done certain things that have elicited the basic probability concepts that we're thinking of. And I already talked about this once, but we're going to kind of roll back over it because it's going to keep coming up. Let's build a sample space. And we're going to make it exhaustive. And we're going to make it exhaustive by way of counting. Okay? So let's say we have S as being composed of a cat, a dog, a fish, and something that starts with a different letter, a rat. We can think of these 4 elements as being numbers in a base system, in a numbering system with base 4. Okay. This is going to give us rationale for what we call a base 4 system. Okay. And I'll be using that kind of language. If we have 4 elements and we're going to try to create an exhaustive sample space given a phenomenon that we're creating, then we are likely going to be thinking in a base 4 system in some way. So if we want to, say, list all outcomes for 4 pets that we randomly select from S. So randomly selected from S. And here's a very important note I'm going to put on here: with replacement. Okay, what do I mean by with replacement? What I mean there is on our first pick, we might choose a cat, and then let's say we put the cat back. We can pick a cat on the second time as well, right? So we could potentially pick cat, 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 when we're choosing 4 pets. Select list all outcomes for 4 pets, randomly selected from S. Okay. So if we think about this like it is a counting system, if we're thinking about this like it's a counting system, each one of these things can be numbers. Cat could be 0, dog could be 1, fish could be 2, rat could be 3. Now, I am not going to use 0, 1, 2, 3 for here. I'm going to use the letters C, D, F, and R. And I just want to show you that we can systematically count this. We could start with, let's say, our lowest number is cat. Then our first four place number is going to be cat, 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 cat. Our next number is going to be cat, 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 dog. Then cat, 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 fish. Cat, 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 rat. Once we get to rat, we're going to need to turn that rat back over and increment cat over to dog. So what we get then is cat, cat, dog, cat, right? I'm not going to write all these out, but I just want to show that this is like counting. Dog, fish, and cat, cat, dog, rat, and so on. We can do this all day. This is like counting. Why is it like counting? Well, imagine we just had a set that was 0 through 9, and we took the same approach. We would start off with 0, 0, 0, 0, then 0, 0, 0, 1, all the way up to 0, 0, 0, 9, 0, 0, 1, 0 is how we would roll that over. It's just in this case we've only got 4 elements, 4 numbers that we're dealing with. So if we want to illustrate, if we want to be exhaustive about this, and we don't want to spend all day with like pen and paper doing it, we can pretty simply do this. This is going to be cat. What did I do? Dog. Ferret. Is that what I did? Yeah, right? Fish, not ferret. Fish and rat. Okay. So we can start with that. Here's our set. We're going to have it be explicitly ordered just for our purposes here, and let us construct all the outcomes of this. So pet outcomes, we're going to collect into an empty list, and I'm going to say for pet 1, right, our first pet selected from pets, and then this is very straightforward, really. It's just going to be pet 1, pet 2, pet 3, and pet 4. And then we can say pet outcomes.append. We can append a list that contains pet 1 and pet 2, pet 3, and pet 4. So let's look at all of these. So for pet outcome, in pet outcomes, which was my collector, we can just print the pet outcome. Oh, I'm in slides, that's why. Okay, so here we have counted in our base 4 system, and this is exhaustive. How many different outcomes do you think there are? Does anybody want to venture a guess as to that? There are this many. But, you know, there is a systematic way to think about this. We've got a base 4 system, right? We've got a base 4 system, so there are 4 elements, and we've nested those 4 elements within 4 loops. It turns out that there's going to be 4 to the 4th power possibilities, which, as was stated, is 256 possibilities. So this this is going to lead us to a very easy way to represent probability, right? We can now ask questions of this. We can ask a question like, what is the probability that a person will select 2 or more cats when randomly choosing 4 pets? So let's answer this. Just going to paste this question in. What is the probability the person will select 2 or more cats when randomly choosing 4 pets with replacement? So let's make a collector, 2 or more cats. And instead of just printing these outcomes, let's look at it this way. Let's say if pet outcome dot count of cat is greater than or equal to 2. Greater than or equal to 2. Then we can collect that into 2 or more cats. And at this point, we have everything we need to answer this question. We just need to know the number of elements in 2 or more cats, right? Which is just going to be the length of it. And we just need to divide that by the length of pet outcomes. And that will give us a probability. Of 0.262, roughly. So, is there a way that we could, in a closed form, answer this question without this iteration? Yeah, probably. There probably is. But this is a method that works, and it's a method that, for very complex probability questions, you can brute force an answer, right? You can brute force this answer. That is not, that's not that hard to do. So let me paste this one in. We're going to look at a number of these kinds of questions from here on out, and we're actually going to use something like this approach to build up ideas around, around counting in general. We're thinking about this as a form of counting, but also we're going to take that into distributions. So from here on out, we're going to be using something like this approach. I'll get more into detail about how to think about this approach, but for the time being, I think we can think about this fairly simply, right? We build a sample space, we create a subset of that sample space using a conditional statement. We collect those elements that satisfy the conditional statement, and we look at the cardinality of the subspace over the cardinality of the sample space, and that is a probability. That is the probability of the subspace event occurring. So let's have a breakout here. You're going to write a function, and that function is going to be based on a function that I give to you called coin flip. So let me paste that in. So your function, series of flips, it's going to have one parameter defined, which is n, and n represents the number of coin flips. Return a list of length n containing n random coin flips. There's a question really quick. Feel free to get started on this breakout. I'll answer this question, and then I'll set a timer for 4 minutes. If we did it without replacement, it would just be the same for loops. but with the added condition that if item not in new list, then append. We'll get to that. We will get to that when we get to permutations and combinations. That is, we're going to build a reductive algorithm from counting. So we're going to take a counting approach. We're going to reduce out the space to permutations, then reduce out that space to combinations to get a very clear sense of how we can derive permutations and combinations. So yeah, that's good insight. Once we start putting with replacement in there, without replacement in there, we're dealing with kind of a different animal. But we can do it. We can do it. Okay, sweet. So I'm going to set a timer for 4 minutes. Go ahead and write this series of flips function. Okay, so let's look at a solution for this. Okay, so from random import choice, and then we have this coin flip function that we're going to extend. So we've got a series of flips, and we want to flip this coin n times, and really we can just do a collector, right? So flips gets empty list for whatever in range n. That's just how many times we're doing this. We're going to append into flips a coin flip, like so. And then we can just return the flips. Okay, so this is a bit of a prelude function to things we're going to be doing later. If we flip this, I don't know, 12 times, we're going to be able to see, right, a collection of heads and tails. And if we wanted to ask a probability of, what is the probability of getting 7 heads in 12 coin flips of a fair coin, we could run this a whole lot of times, right? Count the number of times we get 7 heads and estimate that out of the number of times that we flipped a coin. And we could build an estimator for the probability of getting 7 heads. Would it be exactly correct? No, not necessarily, unless we, performed this, ran this enough times that we happen to get the correct probability. If we wanted to know the answer to such a question exactly, there are a couple ways we could do it. The way that we've learned how to do that up here is we could do a nested, we could do 12 nested loops, right? And count, count from all tails up to all heads. And you can imagine there's some computation time involved with that. It's something we can do, but, we could instead take a sampling approach like this and estimate that. We'll talk more in quite a bit more depth about sampling versus counting. And we're going to get back to counting. So you're going to write a function called let's take a break. Let's take 6 minutes, and when we get back, we'll work on another function. So I'll just set our timer here, and I will see you all back here in 6 minutes. Okay, so we're going to jump right into a breakout where you are going to write a function. And that function is going to be called for-flip sample space. You are not going to use the prior function, right? Now, you could try to use the prior function, but what we want here is an exhaustive approach. Let's say the nested for loop approach. So I'm going to put 4 minutes on the timer. If you need a reference point for how to write this, you can you can go back and look at the, which function was it? You can look at the code where we traversed and did the pet outcomes if you need a hint as to how to do this. So I'll go ahead and set 4 minutes and go ahead and try to solve this. Okay, so a number of you got the solutions on that, and those all look good. So let me just write a quick solution, and I'll talk through it as I go. Okay, so this is called for flip sample space, and a single flip is going to be a heads or a tails in this scheme, and we're going to collect those outcomes in a list. So for flip 1 in flip, let's say let's call this flips, and then we'll do 2, 3, and 4. And for each of those, we can say outcomes.append, and we'll append flip 1, flip 2, flip 3, and flip 4. Of course, I have to update all these names. So that one is 4, that one is 3, and that one is 2. Okay. And then we can just return the outcomes like that. If I want to get these out of here, of course, I can call the function for flip sample space. Oops. And we can traverse this for each outcome. In the outcomes, let's print that outcome. So this particular one, that is not very readable because I'm printing outcomes a bunch of times, not the single outcome. Okay, that's better. This is a base 2 system where our symbols are heads or tails. And since it's base 2, and we've got 4 places of it, we have 2 to the 4th power, or 2 times 2 times 2 times 2, right? Which is 16 possibilities between all heads and all tails. This is binary, actually. Clear as anything, we've got a base 2 system, which is binary, and this is exactly how we count in binary, but we use different symbols. Okay. So I think we're going to extend this a little bit and do another breakout, and I'll give you, I'll give you this code for anybody who didn't get to a solution. And I'll just put the breakout up here to start. Okay, so you're going to answer this question, and really, what is the probability that in 4 coin flips you get exactly 3 heads? So you could answer this programmatically, right? You could traverse the data, the outcomes data. You could also consider, oops, I just made that disappear. Now, this says 4 minutes. Let's do 3 minutes. And yeah, just answer this question. You can either do it programmatically using Python, or answer it outright. Either way is fine. Okay, so how many outcomes do we have? Well, we have 16, and 4 out of those 16 have exactly 3 heads, right? So we could just say this is a probability of 4 out of 16, or 0.25, right? We could do that. We could also collect into some, collector, and I'll call that 3 heads. So following this same pattern, so for each outcome, in outcomes, we could say if outcome dot count of heads is 3, then we can collect that into 3 heads. So append that outcome, and then we can look at the cardinality of 3 heads, right? The length of 3 heads over the cardinality of our outcomes, the cardinality of A over cardinality of S, however we want to think about that. So let's just verify that I'm not egregiously wrong. It's 0.25, right? It's 4 out of 16, or 1 out of 4. That's a fairly easy one. We can see that very clearly, but we want to be building this idea of probability from a couple different angles. There's the angle of, well, can we compute this without a procedural Pythonic or procedural Python approach? That one we probably could have. We could have counted them all out and looked at how many have 3 heads. We could have done that pen and paper without much trouble. But let's think of a different problem. And let's say we have, let's harken back to that series of flips function. Right? Remember, series of flips, we can pass in some number, n, and we're going to get heads and tails back, randomly generated. So let's think about a series of flips with 14 as the number of flips. Let me see. Okay. All right. So let's think about a series of flips, 14, and I'm going to ask a sort of special question here. What is the probability of getting all heads? Getting all heads values. So what is that probability? Does anybody have a guess at that? Just offhand, without programming, without anything. Does anybody have a thought on that? So there's a guess here that is 1 out of 14, 1 out of 16. Neither of those are correct, but I understand the intuitive jump to that. 1 over 144 plus. Okay. Let's think about this from a couple different angles. So first off, what is it going to take for us to get, okay, yeah, somebody called it, right? So for us to get 14 heads in a row, what does that look like? It looks like heads, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, this is, if we're thinking about this in terms of that counting approach that we looked at before, we could build something with 14 nested loops, right? We could do that. But let's think about this as, these are all heads. So, this is our 0th instance. This is our first instance. This is going to be all heads and then a tails, right? And then this is going to be heads and then a tails, heads, and so on. until we get to all tails, right? And, you know, eventually we have all tails. Well, this is a base 2 system, right? This is base 2. And we're talking about 14 places of base 2. How many possibilities are there in 14 places of base 2? Yeah. Close. The response I'm seeing in, there we go. That's it. Exactly. Right. So we have 2 to the 14th possibilities, right? There are 2 to the 14th of these. There are 2 to the 14th possibilities, and there is only one that has all heads. So we don't, to answer this question, we don't actually need to do any counting. There are 2 to the 14th possibilities, and one of those is this all heads that we're seeing here, right? So this is 1 out of 2 to the 14th. Pretty straightforward. We can turn this on its head a little bit, and instead of thinking about it in the totality of you know, all the different possible permutations, or, you know, all the different ways that we can have heads and tails happen. These wouldn't be permutations, they'd actually just be counting. 1 over 2 to the 14th is the same thing as 1/2 to the 14th, which is the same thing as this first trial, 1/2, times the second 1/2 times the third, right? 1/2 and so on, 14 times. And so the implication here is that, n implication here, okay, n implication is that this first flip, this first heads that we get, does not affect the second heads, does not affect the third heads, and so on. These are all independent from each other. And we can take this further. We could say, okay, well, how do we answer the question, what is the probability of getting all heads in 4 flips? Well, that's just 1 over 2 to the 4th, right? We could take this further and ask a question like this. We could ask the question, what is the probability of getting this sequence, of getting heads, tails, tails, heads, tails? What is that? What is the probability of that? We can start seeing this is really the same problem. Again, exactly. It's either, however you want to express it, it's either 1 over 2 to the 5th, or it's 1/2 to the 5th. Either of those ways of representing this is true. And, you know, so we can take the result of the first flip, multiply it by the second one, by the third, by the fourth, by the fifth. So this is one type of question. What is the probability of getting this specific outcome? This is one instance out of all those instances, right? So there's another question, another type of problem that looks sort of like this, but you're going to have to be careful with this. Well, before we get there, let's back up to that idea of all heads in 14 flips, right? So 14 heads. So this is 14 heads, right? And we established that was that's 14 heads out of 14 flips. That is just 1/2 to the 14th, or 1 over 2 to the 14th. What about the probability of at least 1 tails? In 14 flips. What about that? It's a very this problem can be directly extrapolated from this, from the probability of 14 heads. What is the probability of getting at least one tails? Yeah, it's the complement. It's the complement. So this is just going to be 1 minus 1/2 to the 14th. And if you think about why that is, right, we've got all these heads, and then, so that's our only instance. There's only one instance where we have all heads, so every other instance has at least one tails, whether it's, whether it's heads and then a tails, or heads and, tails heads, however that comes about. So these two questions are pretty easy to answer, right? The probability of a specific instance, that there's only one way for that to occur, or the probability of all heads in this instance, or what is the probability of everything else, and that's just 1 minus that, right? So those two are pretty straightforward, but you want to be careful. There is a type of question where there's a type of question that won't be as easy to answer, okay? And we want to be careful about this. So in 14 flips, what is the probability of 5 heads? Right? That's a different problem. Now, why is that a different problem? Let's think about a bunch of different ways to get 5 heads in 14 flips, right? We can have tails, 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 5, 6, 7, 8, 9, and then heads, 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 right? That's one way. We could have tails, and then this one, make this one a heads, and that one a tails, that one a tails, and then heads, 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 heads. And we have to really start thinking of all the different ways that we can arrange 5 heads over 14 flips. We have to construct that subset if we want to be able to answer this question, and that's not as easy. We're going to take a reductive approach to answer that question, but just, fundamentally, it's not as easy of a problem. And so, let me look at that question. How do I explain the complement? The complement is like everything else, right? So let me finish this thought, and I'll come back to the complement. If we want to be able to answer this question, the probability of 5 heads in 14 flips, we would need to create an exhaustive set of outcomes where there are exactly 5 heads in 14 flips. That's going to be a bunch of different arrangements of heads over 14 instances, right? And we don't know what all those are. We don't have a systematic way at this point of doing that. I'm going to show you a systematic way of doing that. Well, we might even get into that a bit today. If we get that far, we'll see. But ultimately, there will be a closed formula called the binomial formula that will allow you to answer that kind of question, and answer it pretty easily. So the question is, how do I explain the complement? At least one tails in 14 flips. Let's think about this in terms of 5 flips, because I think it's easier to see that. For 5 flips, so we have this one instance that is all heads. There's no tails in that. This is the only instance in 2 out of in 2 to the 5th instances, right? So this is the only instance that does not have a tail, right? So there's no tail. There's no tails there. Everything else does, right? However we arrange this, heads, 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 tails. I mean, I could just count here, right? Heads, 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 tails, heads. You know, next one would be tails, tails, right? And so on. Any one of these has at least one tails. So the complement in this case, if we put focus on this all heads, the complement is going to be everything else that's in the set, right? It's going to be everything else until we get to tails, 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 tails. So if we think about that in terms of, you know, of S, we have one instance in S that represents our point of focus, right? Whether we call this A or let's call it H for all heads. If we want to find out the complement of H, it's going to be everything else, right? And in this case, everything else can be defined by having at least one tails. Yes, A and not A are complement to each other. If it is so, is it correct to say the probability of A and probability of not A are complements to each other? Yes. Yeah, that is correct. Yeah, and so the probability of all heads, right, is going to be exemplified by 1 over, in this case, 2 to the 5th. So 1 over 2 to the 5th plus, we could do this, 2 to the 5th minus 1 over 2 to the 5th. I don't think it's too hard to see that this is just 2 to the 5th over 2 to the 5th, which is 1, right? So, you know, if I just wanted to write this a little further, this is going to be 1 plus 2 to the 5th minus 1 over 2 to the 5th. And obviously 1 minus 1 is 0. And we're left with 2 to the 5th over 2 to the 5th, which is 1. So, yes, A plus not A is going to be, if we're talking about sets, well, that's going to be the entirety of our sample space. If we're talking about probabilities, the probability of A plus the probability of not A, that's going to equal 1. Cool. All right, so that pretty much wraps it up for basic probability. Let's look at the next set of materials. So we're gonna work ahead, which is kind of nice. Let me answer that question before we move on. I'm making this distinction between what we're calling basic probability and probability that's going to take a little more work or a little more specialty in terms of the functions we use. If we're talking about the probability of all heads, right? Or let's say we have a sequence of events where we can just take the probabilities of each of those points in the sequence. We can just multiply all those together to get the probability of those occurring in sequence. We can do that. That's what we're doing with the probability of all heads. If we think about it like in 14 heads, you know, this is just 0.5 times 0.5, 14 times, or, you know, more succinctly, 0.5 to the 14th power. The probability of no heads or all tails would be the same thing. The probability of at least one tails is just going to be, you know, let's say greater than one tail is going to be 1 minus 0.5 to the 14th. So those are easy. They're basic probability, or the probability of a specific sequence of heads and tails. That's pretty easy. It's just going to be 0.5, again, 0.5 to the 14th power. We can figure that out without needing much more than what we've got here. However, if we're asking the question, the probability of 5 heads in 14 flips, that is more complex because there are different arrangements, there are different ways that we can get 5 heads in 14 flips. And so we need to take a different approach. We either need to determine all those different ways and count how many different ways we can do that and divide that by 2 to the 14th, or we need some other formula. Turns out there is a formula that'll answer that for us, for this type of problem. But of course, there are other types of problems, and they may require a more nuanced approach. Something that, like let's say we're dealing with, I don't know if you've ever seen a 3-sided die, but it's sort of like a stick that you can throw, and there's only 3 possible ways of that stick landing. In that case, let's say we could either get a 1, a 2, or a 3. If we throw that die 14 times in a row and ask the question, what is the probability of getting 3 2s and 1 3 in that approach, that's a harder question to answer. We can't answer that so easily. What we could answer is, what is the probability of getting all 1s? Right? That's a different thing we can answer. That would be 1 over 3 to the 14th. That's easy to answer. Or all 2s, right? Or what is the probability of getting all 1s? What is the probability of not getting all 1s? Is a question we can answer, because that would just be 1 minus 3 to the 14th, right? So some probability questions, so you have to really you have to think about this up front. You have to put that thought in and say, and ask yourself, is this something that is simple to answer? Is it something that's complex? Because, for example, this 5 heads in 14 flips question looks a lot like getting all heads in 14 flips, or getting at least 1 tails in 14 flips, but it is a sort of fundamentally different problem that takes a bit more work. So that's hopefully that clarifies that, and we're going to spend some time on it. So the question is, am I talking about permutations or combinations? That'll become more apparent pretty quickly here. So we're about to get into permutations and combinations, and the way that I would think about this is there are a certain number of ways that we can permute 5 heads over 14 flips. When we get down to it, we're going to be thinking in terms of combinations, because the order doesn't really matter, right? We're counting how many different ways we can get 5. But if we're talking about all the different ways that 5 flips can occur, and we're going to divide that, say, by the number of possible ways that, the possible flips that can occur, then we would determine this probability by way of permutations, permuting 5 over 14, dividing that by 2 to the 14th. However, when we use the binomial PMF, when we use the binomial formula, we're going to use combinations in there, because we're trying to just determine how many different ways, or how many occurrences of 5, 14 choose 5 there are. So that those are sort of 2 different ways of thinking about the same problem, but we're going to think about that same problem in different ways. Okay, so let's look at let's start getting into counting. Let's get into the slides, and we're looking at, where's this? Statistical counting, yep. Okay. So we've been counting. We've been looking at ways of counting. And I've been trying to make that pretty obvious, right? That we can think of elements in a set as being something like numbers. They're symbols that we can use to count to make an exhaustive list of possible outcomes. So far, we've done that with replacement, right? You know, cat, we can get cat, 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 or cat, 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 dog, cat, 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 fish, and so on. That's like counting in a base 4 system. We're going to take that idea further and consider concepts that, so statistical counting. We're going to consider scenarios where we don't have replacement, where we get rid of this idea of replacement. So there are 3 concepts that we're going to focus in on. We're going to look at factorial, we're going to look at permutations, and we're going to look at combinations. We're going to take a few different, just a couple different lenses on these. Okay, so first off, factorial is a special case of permutations. It's also a very basic function that we're going to use in our permutations calculations, and that we're going to use in our combinations calculations. Factorial shows up all over the place. It's one of those functions that offhand, you know, should take you, 30 seconds to write. It's just something that you should be able to pull out of your head. We're not going to ask you to write the factorial function on the interview. We'll let you just import it from the math library. But it is a function that I'm going to have you write multiple times as we go forward in this course. So let's sort of, we probably have enough time to talk about factorial in the next 15 minutes, and then we'll table permutations and combinations for our next class tomorrow. So factorial is easy to represent. We just use an exclamation point. The way that we're going to see this in code is just factorial, right, of n. Easy concept to get. So if we have 5 factorial, this is just going to be 5 times 4 times 3 times 2 times 1. So why factorial? Why? What does this represent? Now, it may not be obvious, but I'm going to try to prove, show this to you. Factorial gives us the cardinality of arrangement of n items. So arrangement. If we have the numbers 1, 2, and 3, how many different ways can we arrange those numbers, right? We could do 1, 2, 3, 1, 3, 2, 2. Well, should try to be systematic about this. In fact, let me be systematic about this. We have these symbols 1, 2, and 3, right? We can start off thinking about this as a base 3 system, where we go 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 3, 1, 1, 3, 1, 3, 2, 1, 3, 3. That'll be 2, 1, 1, 2, 1, 2, 2, 1, 3, 2, 2, 1, 2, 2, 2, 2, 2, 3, 2, 3, 1. If you see me make a mistake, please point it out. 2, 3, 2, 2, 3, 3. And then 3, 1, 1, 3, 1, 2, 3, 1, 3, 3, 2, 1, 3, 2, 2, 3, 2, 3, 3, 3, 1, 3, 3, 2, 3, 3, 3. I'm not recommending this as your approach to figuring out factorial, but I'm just making a point here. So if we want to reduce this space, we can reduce it by getting rid of any of these. So our reductive approach here, let's get rid of duplicates, right? So we're going to reduce through deduping. So 1, 1, 1, that's not good. 1, 1, 2, 1, 1, 3, no. 1, 2, 1, no. 1, 2, 2, 1, 2, 3. Well, 1, 2, 3 seems to work. And 1, 3, 1 does not. 1, 3, 2 seems to work. I probably won't select the same color, but that's okay. 1, 3, 3, 2, 1, 1, 2, 1, 2, 2, 1, 3 seems to work. 2, 2, 1 does not. 2, 2, 2 does not. 2, 2, 3 does not. 2, 3, 1 does. I think you get the idea here, so I'm just going to start circling the ones that have all uniques. And let's see how many there are. 3, 2, 1. 3, 2, 3, 3, 3, 1, 3, 3, 2, 3, 3. Okay. 1, 2, 3, 4, 5, 6. There are 6 of those that satisfy having all unique elements. And we can see that these are all different arrangements of the originals, right? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. This turns out to be 3 times 2 times 1, which is 6. There are 6 of these. So this is our cardinality of arrangement. We can see it pretty clearly as that. Now, let's put a story to this. Let's think about this in terms of a specific story. Let's say we have a bag, and there are 3 balls in this bag, right? And we've got 1, 2, and 3. Okay. So if we want to think about our first draw, so here's draw 1. We're going to reach in and we're going to pull a ball out. We're either going to get a 1, a 2, or a 3. And then we've got draw 2. We only have 2 options at draw 2, correct? So if I drew 1 on the first draw, I can either draw a 2 or a 3. If I drew a 2 on the first draw, I can either draw a 1 or a 3. If I drew a 3 on the first draw, I can either draw a 1 or a 2. And then there's only 1 ball left on the third draw, so 1, 2, if it's 1 and then 2, then it's going to be 3. 1, 3, it's going to be 2. 2, 1, it's going to be 3. 2, 3, it's going to be 1. 3, 1, it's going to be 2. 3, 2, it's going to be 1. So we have here 1, 2, 3, 4, 5, 6 different ways. We can see that very clearly. There are 6 different ways of arranging. So factorial gives us what we can consider to be the cardinality of all the different ways we can arrange drawing items without replacement. So what I'm going to have you code, I think we have just enough time to do this. I believe we're in perms.combs.py. I'm going to have you code the factorial function, and that's how we will wrap up today. It says 3 minutes to code this. I'm going to put 4 minutes here and just have you code this out. It's, oh, no, I should probably get us back into the source directory. Oh gosh, is this 4? Yep. Okay. So go ahead and code the factorial function. It's, of course, it's going to have one parameter. That's the number you're passing in. And all it's going to return is, if you pass in 5, it's going to return 5 times 4 times 3 times 2, which is going to be 120, for example. So go ahead and code that up. Okay, so This is one of those functions that, like I said, should generally just take you, should be a pretty instant function to write. So factorial n, I'm going to start with a product of 1. I can't start with 0 because 0 will just zero everything out. So I'll say for num in range, we're going to go, I can start at 2. I don't need to start at 1 because anything times 1 is just itself anyway. I can go to 2, from 2 to n plus 1, and I can increment the product accordingly by num. Return the product, and what we should see when we run factorial of 5 is 120. So let's try that. Print factorial of 5. And that is 120. So there are 120 ways of selecting, 5 balls out of a bag if those balls are numbered 1, 2, 3, 4, 5. There are 120 different ways that we can do that. Factorial gives us that cardinality. So let's stop there. I don't want to jump into permutations, which is next, without giving it more than a minute or 2 minutes. But what I will say is that factorial is a special case of permutations. And as you can see with factorial, the order is important. We are looking at all the different ways of ordering these 5 objects, right? And in that sense, we are very concerned about the order. So we'll take that idea into permutations. Permutations, in its most basic form, is just factorial. But we might be trying to ask a different question, like, okay, you have 10 objects. How many different ways can you arrange 5 of them? And that would look like, the way we would probably notate that is simply with something like this. 5 permute, sorry, not 5 permute, 10, but 10 permute 5. So there are 10 objects. How many different ways can we arrange 5 of them? There's a systematic way that we can look at that, and there's a closed formula that will give us an answer to that question. Awesome. So that's class for today. Give me just one moment.